Hello, I am Chandima Fernando, and welcome to my presentation on co-regulated information consensus with delays for multi-agent UASs. My advisors are Dr. Justin Bradley and Karim Detweiler. Our funding sources are at the bottom of the slide, and we are very thankful to them. We are part of Nebraska Intelligent Mobile Unmanned Systems Lab, or NIMBUS Lab, from University of Nebraska-Lincoln. We work on environmental monitoring through multi-agent unmanned aerial systems, or UASs. One of the examples is wetland monitoring, which helps to manage a healthy ecosystem around them. Wetlands are very sensitive to external disturbances. Hence, employing a group of human researchers to observe these sensitive environments would be very costly, time consuming, and most importantly, harm the fragile ecosystem. We propose to use a group of UASs to monitor the wetlands. Using a group of UASs disturbs the environment the least, reduces human involvement, and covers a large area in less time. To manage a group of UASs, we want to use consensus algorithms. Consensus algorithms are well suited to coordinate a multi-agent systems to agree upon a common value. However, the transition of a consensus algorithm from being a mathematical equation on a paper to a binary implementation on a processor inside a UAS is very challenging. One of the biggest challenges is the resource limitation on a UAS. We focus on two such limited resources on a UAS: computation resource limitation and communication resource limitation. The UAS will be equipped with cameras and other sensor equipment that gather a large amount of data that needed to be processed. This requires large processing power. Now we need to optimize the processing power to get the maximum utility out of the limited processing power. This is challenging. The other limited resource is communication. Bandwidth is limited on a UAS. It is now asked to communicate with multiple other agents around it to reach a consensus. This requirement becomes steep when the value of the agents agreed upon becomes a multidimensional array of values rather than a single variable. Therefore, it is important and challenging at the same time to manage the limited communication resource. On top of resource limitations, real-world systems inherit delay. This delay can be internal, where there's a time difference between the sensor data being recorded and processed in the processor. Or the delay can be external, where there is a time difference between the time of the transmission time from one agent and the receiving time of the agent at the other end. Hence, the solutions we derive for the key challenges must account for these delays as well. Therefore, our efforts in this paper focus on these key challenges: how we can intelligently manage resources in a multi-agent consensus setup, and how to translate these theoretical algorithms to practical implementations. Towards solving the key challenges, this paper presents the following two key contributions. One, we propose to co-regulate both the communication frequency and agent's physical position to have a desired level of performance while saving resources. Two, we propose an architecture to implement co-regulation algorithms on a UAS. Here is the basic discrete time consensus algorithm we use on each agent. Capital I denotes that X is the information state. Simple I denotes indexes of the agent. K is the discrete time index. Wij is the weight of the connection between agent I and agent J. Capital M is the neighborhood of agent I, and tau is the delay. First, let's discuss co-regulation on communication frequency. We propose to dynamically change the communication frequency when it is needed. Here is the equation that calculates the control input to the communication frequency. Alpha 1 and alpha 2 are two controller gains that can be tuned to control the aggressiveness of the frequency change. When the agents receive a new state update from its neighbor, there will be a difference between the agent's state value and the new consensus value. We utilize this difference to increase the communication frequency and communicate the new state to the other agents at a faster rate. This helps in faster convergence time in the network. Similarly, when that state difference diminishes, we reduce the communication frequency and save computation resources where a fixed controller would have not achieved. Our theoretical proofs account for the communication delay as well. We refer an interesting reader to our paper for complete proof. Now let's focus on co-regulating agent position. Similarly, we regulate agents' physical position on the field to achieve faster convergence times. A communication device's range is limited, and the number of neighbors one agent can have become a function of how far the agent is located away from the other agents. When an agent receives a new update on the state value it consensus on, again there will be a difference in the new consensus state and the agent's own state. Now we apply another consensus algorithm on the agent's physical position and calculate a consensus position on an agent and its neighbors. Then we move the agent towards the consensus position. Thereby, as long as there exists a state error in the original consensus value, the agents keep calculating their consensus location and move towards it. This pushes all the agents closer and creates more neighbors for each agent. This leads to faster convergence. Once the state difference diminishes, the agents are moved back to their original starting locations. Let's look at a MATLAB simulation example where we simulate a scenario with 6 agents. All agents' information states are initialized at random to be between -5 and +5. They start with an initial frequency of 0.2 Hz and have a lower and an upper limit of 0.1 Hz and 1 Hz respectively. Their delay varies between 0 seconds to 6 seconds. Their initial physical locations are a ring-like shape as seen in the image to the left. We let the connectivity between the agents to be minimum, where one agent's communication range only allows it to talk and listen to the agents beside it. This creates a ring-like topology. We simulate the system for 40 seconds. You can see how the frequency is increased in the beginning when there is a difference in the information state. The frequency is decreased when the information state difference between the agents diminish. The increase in the connectivity plot is a result of the agents moving closer when the information state difference exists. These 3 graphs show how the consensus on the agent's position changes and how they are moved back as the information state differences decrease throughout the simulation. Let's focus on our second goal of implementing these co-regulation consensus algorithms in UASs used in practice. For that, we developed the following architecture that separates the consensus controller from the vehicle controller. The consensus controller would apply the co-regulation strategies on top of the consensus algorithms to find out the waypoints in space where the UASs should move to. These waypoints are passed to the vehicle controller. The vehicle controller will then move the vehicle to the respective waypoint. This helps us to easily deploy our algorithm on a variety of vehicles, irrespective of the different low-level controller in each of the UAS made by a different manufacturer. Here is one of the 4 flame wheel for 50 UASs we used for our experiments. We have added a Pixhawk flight controller for low-level maneuvers. We used an Odroid XU4 single-board processor for in-vehicle computation of the consensus algorithm. We used an Zigbee device configured to broadcast and receive messages from multiple agents. Here are the state convergence plot and the real-world positions plot on the outdoor experiment we conducted with 4 UASs. We refer the listeners to the paper for more details. Thank you.